Well, this is where we're going more in depth. All right. So let's go ahead and look at this journal. So first things first, we do have our I can statement, which I don't have a box for it, but just write it somewhere either above or in your journal itself. So this is lesson 9.1, and the I can statement is I can fit a regression line to linear data determine direction and strength of the correlation and use the fitted equation to solve problems. So again, we saw this, we talked about this briefly back in the last units we talked about with quadratic regression. We have talked about linear and exponential regression before back in unit 6, but what we focused on solely with both of those lessons was just getting the regression line. All right. Now we're actually going to look at how that regression correlates to the data that we're given, meaning how it relates to it or how closely it relates to it. It's also going to help us solve some problems. So we did this a little bit with the quadratics where we were plugging stuff in for x and, evaluating it. That's what I really mean by solving problems. All right. Now, specifically with the regressions, we're going to be looking at scatter plots as well. Now, you guys have heard the word scatter plots before, probably back in middle school, maybe early elementary school. Can anyone tell me what a scatter plot is? Embry. Kind of, sort of. Elise, what do you got?
It's the points that make the lines for a scatter plot that makes it linear.
Kind of. Anyone else know what a scatter plot is? So a scatter plot, it's kind of in the name. Basically, it's a bunch of points that they're all kind of scattered around the graph. And there's really no direct relation, meaning that we can't just draw a nice straight line through them. All right. So for example, the one on the front page, this would be an example of a scatter plot. We could not easily draw a straight line through all those points to make a nice consistent function. It would look like something like a really bad zigzag or some maze or something. All right. So let's go ahead and look at just writing a prediction equation. So this is kind of the getting the regression equation. We're just going to try and write an equation to predict values. So some vocabulary first. So data with two variables is called bivariate data. All right, and it's kind of the name. Bi meaning two, variate meaning variables. All right. Now, a set of bivariate data graphed as ordered pairs is a scatter plot. So that's the more formal definition of scatter plot. Now, you can use a scatter plot to determine what we call correlation or how the two variables relate each other. So these two variables may be representing something different. So for example, speed and distance or time and height, things like that. All right. They don't necessarily have a direct relationship, but they could have a correlation or a more vague relationship. All right. So a direct relationship would be we can draw a line straight through the points on the scatter plot and it would look like a linear function. A correlation means that it's really, really close to our line of best fit. All right. Now, there can be a positive, negative, or no correlation between variables, and we'll talk about what that looks like in a little bit. And correlations are typically described as either strong or weak. So, in a strong correlation specifically, the points of the scatter plot are closer to the graph of a line than the points of a weak correlation. So, we'll look more in depth at what that looks like in a little bit. All right, so for right now, we're just getting through some vocab. Now, we then have what we call a trend line. Now, you guys know what a regression line is. A trend line is typically the line that we predict if we're doing it by hand. All right. So the calculator gives us the most exact regression or trend line, whereas a trend line, if we did by hand, is one that we made ourselves. So a trend line is a straight line that comes as close as possible to the points on a scatter plot. So there are approximately the same number of points above and below the line of the trend line. This is also called the line of best fit. So that's another name for a regression line that we have also talked about. Now, the equation of a line best fit is called the prediction equation because it can be used to predict one of the variables given the other. Now, on top of that, we have what's called an outlier. Now, an outlier is essentially a data point that doesn't appear to belong to the rest of the data set. So, for example, have you guys ever had teachers where they've said that they would curve a test grade based off of how well you guys do on it? All right. So, a lot of times what teachers do when they curve is that typically, like for example, if it was me, I would want to curve if, say, most of you got between the 60s and the 70s. All right. Now, the way I curve, I use a formula. However, that formula does not work if I have an outlier. So, in other words, if almost all of you got a 60 or 70, in between 60 and 70 on a test, an outlier such as, if someone got 100, would what we call skew the data, meaning that it would shift it so that it would actually not curve in you guys' favor if you had a 60 or 70. All right. It'd be more in your favor if you had like an 80 or 90. All right. So essentially what we do is we take the outliers out so that it's a bit more fair. All right. We also take out some lower outliers. So like say if it was like, the average was like 60 or 70 and someone got like a 10. All right. We take that one out too because it's so far away from most of the data. All right. So that's what an outlier means. It just doesn't belong in the rest of the data set. It's kind of like it just happened. It was like a once in a blue moon. Just you got lucky. It just happened. Now to find the trend line. So again, this is the only part that we do by hand, and to be honest, we won't ask you to do this often, but you may be asked this on the EOC. So to find the trend line, we're going to use 2 points that seem to represent the data well and write an equation. So typically you want to pick 2 points that are kind of in the middle, all right? And since it's based on your judgment of what points that you think are best, your line may be different from someone else's trend line. So if I just gave you a problem and I said find the trend line based off of these points, but I didn't tell you which points to pick, depending on which points you pick, your trend lines could be different. All right, because there's no exact or direct relationship between the points. So it's not going to be a perfect linear function. It's not going to be a perfect quadratic function. All right. So let's look at an example of that. So I have to jump around because of the way my PDF is, but y'all are still good where you are at. So let's look at this first example. So a table below shows the years of experience for 8 computer technicians at CompuNow and the hourly rate of pay each technician earns. So the experience in this case would be your X, the hourly rate would be your Y. Now, we're just going to draw a quick scatter plot of these points to describe the hourly pay. So your Y values would be right here, and that will represent your rate. Your X values would be here, and that would represent the year. Now, the way you scale your scatter plot, it doesn't really matter. It's up to you how you want to scale it. But I'm going to scale it like this. So like every other line on the y-axis is going to be 2. So that means every line on the y-axis is going to be 2 units. So every other one would be 4. So I'll label it like this. And then every line would be 1 unit on the x-axis, so every other would be 2. All right. Now, if we plot the points, which I'm just going to do it very quickly for time's sake, it will look something like this. So plot them as best as you can, matching mine. So it doesn't have to be perfect, just do it as best you can. All right. So if we plot them, and again, it doesn't have to be perfect, it would look about like that. Now, while you guys are plotting, if you're looking at mine, does that look like it would create a linear function? So can anyone tell me what a linear function looks like? It just looks like a straight diagonal line. That's all a linear function is. That was like predominantly what we learned back in last semester. So does that look like it could be pretty close to a linear function? Not going to be exact, but does it look like it could be if we moved like 1 or 2 points? Yeah. So we're going to say that our trend line should probably be of the linear variety. So once you graph your scatter plot, what I want you guys to do, and it doesn't have to be perfect, but I want you to draw where you think the regression line would be, or the trend line. So I think it would be about right here. And again, it doesn't have to be perfect. It's not going to go through all the points. We just want it to look like you're going to have some above the line and below the line. It's not going to be perfect, but we just want to represent what possibly could be where the trend line is. All right. Now, looking at the correlation. All right. First off, do you think this will be a positive or negative correlation? Positive. Why? Right, because it's a positive slope of the line. So I would say that this is positive. Now, look at how close the different points are to that trend line. The closer they are, the stronger the correlation. Do you think this is going to be a weak or strong correlation? I would say pretty strong. Those points are pretty close to that line. So I would say this is a positive, strong correlation, which essentially means that there's a high chance that these two variables, so the year of experience that you have and the hourly rate of pay, are pretty highly related. All right. So guys, with your heads up, come on. Heads up. Come on. You can have heads up or you can stand up. Those are the two options. So come on. Now, we're going to write a prediction equation to show how many years of experience are related to hourly rate of pay. So, we're going to do this by hand. So, we're not going to actually get the regression equation. We're going to write a prediction equation, which means we're taking some points and coming up with our own line. And it's not going to be exact. It's not going to be probably even close to what the regression actually is. It's just what we think will happen. So, first off, just to review, what is the slope-intercept form of a linear function? Y equals mx plus b. So this is what our equation is going to be in. What's m represent? What's b represent? The y-intercept. Now, does anyone remember how to find the slope using 2 points? If we're not given the graph.
The x. I don't know what it's. It's just another formula. Can I write it?
Oh, you're so close.
X2 minus x1, and then y2 minus y1. I just said that.
You're close, they're just flipped. So to find the slope, m would be equal to y2 minus y1 over x2 minus x1. All right. So you had it, it was just flipped. Very, very close. All right. And another way you can think about it is your y's represent your rise because it's going up or down, and your x's represent your run because it's going from side to side. All right. That's another way you can remember it. So let's just pick some 2 nice points. So if we look at our scatter plot, which 2 points do you think would make a pretty decent, like goes through our trend line pretty well, Elise?
6 and 12 and 2 and 10.
Yeah, I would say 6 and 12 and 2 and 10. Those look like some pretty decent points. So those would be the points that are right here. So 2 and 10. Nope, that's not the point. I definitely marked the wrong point. So I would say 2 and 10 and 6 and 12. All right, that's kind of pretty decent points. So let's use the formula. So we're using the points 210 and 612. Let's put it into our formula. So which point do you want us to be our x1, y1, and which one do you want to be our x2, y2? Right. So I would say 2 would be x1, 6 is x2. So where does y1 go with? 10. And so y2 is 12. And so we're just going to put those straight into the formula. So I have 12 minus 10 over 6 minus 2. So what's 12 minus 10? 2. What's 6 minus 2? 4. What does that 2 over 4 simplify down to? 1/2. So my slope, or m, would be about 1/2. But we're not done. We then need to find our y-intercept based off of those 2 points. So we currently have y equals 1/2 x plus b. Does anyone remember how I can use a point to find the y-intercept if I have the slope? Good. So you would take one of those 2 points, it doesn't matter which one, and you would plug in the x value for the x and the y value for the y, and then you solve for b. So I'm going to use the 2 and 10 because it's smaller numbers. So I'm going to take the 2, plug it in for the x, and the 10 and plug it in for the y, and then we're going to solve for b. So that would look like 10 is equal to 1/2 times 2 plus b. Then we just have a very simple one-step equation after we simplify. So first off, let's simplify. What's 1/2 times 2? So think about it this way. What's half of 2? 1. That's the answer. All right. So 10 is equal to 1 plus b. Now how do I get the b by itself? Subtract 1 to both sides. Good. So b in this case would equal 9. So if I was to write my prediction equation, I would say that it looks like y equals 1/2 x plus 9. That's what I would say my prediction equation is. Now, will that probably be even close to the regression if we put in the calculator and took it? Probably not. But that's what we predict would best represent our trend line that we drew ourselves. Guys, heads up. Come on. Last warning or you're standing. So now that we got the equation, let's use it to figure out this next question. So using that prediction equation, how much do you think a technician with 15 years of experience would earn per hour? So how do you think I'm going to find this? First off, what information did they give us? They gave us the what? The 15 years of experience, right. Does that represent an X value or a Y value in this case? It represents an X value. So we're saying that X is equal to 15. And I'm trying to find Y. So if we know X, that means we're trying to find Y. If we know Y, we're trying to find X. So given that, how do you think I'm going to find that Y? Using the equation I just found. Please. Right, we're going to take this 15 and plug it in for the X value and evaluate. All right, so I would have Y is equal to 1/2 times 15 plus 9. All right, so take a minute, put that in your calculator, tell me what you get. Be what? 7.5. So we're saying that Y is equal to 7.5, which in terms of money, what would that be? $7.50 per hour. Now, let me ask you this. Look back up at what we have. Did I do something wrong?
No, he didn't finish. Right. He was halfway telling you his answer.
Oh, okay. So yeah, it's 750. That's 15 over 1/2, and then plus 9, that would be 1650. So we're saying it's about $16.50 per hour. Now, let's just think about this real quick. If we look back at our chart up here, does that seem like a plausible answer if we have 15 years of experience to make $16.50? No, why? Why do you think? Right. So if you think about it, if you have 9 years of experience, you're making $17 an hour. 10 years of experience, you're making $17 an hour. So you would think the more experience you have, the higher you'd make. But if we're working 15 years, we're making $16.50. We got demoted at some point. We went down. All right. So our trend line that we found by hand is probably not the best equation to predict the relationship. But that's okay. That's what we just want to do. We just want to see if we would predict. All right. Now we're going to look into the area of actually taking the regression and find the relationship. So let's look at the vocabulary section on the next page. Yes, sir. Quickly. All right. So another method for writing a line of best fit is to use a regression. So we've already talked about regressions before. All right. So remember, a regression line is determined by ensuring that the distance from all the data points to the regression line are at a minimum. So in other words, we want the closest possible line that we can make that the distance between the points and the actual line itself are about the same. All right? As close as we can get. And remember, regression lines, you have to use your calculator to find them because we want them to be exact. All right? So, the correlation coefficient, or R, this one I've mentioned in passing when we talked about linear and exponential, but now we're going to actually go deeper into it. So the correlation coefficient. So do you guys remember how when I made you guys get the regression that it would have like the A, B, and C, and then you'd see like R squared and R? All right. That's what that R value is. It's called the correlation coefficient. The R squared is called the coefficient of determination, but we don't really use that in this class. All right, we're solely focusing on the correlation coefficient or just the singular R. And that data shows, the correlation coefficient shows how well the data is modeled through the linear equation or how strong the correlation is. And typically, it's a number between -1 and 1. All right, so not only does it tell us the strength, it also tells us the direction, so whether it's positive or negative. All right, so when R is close to -1, we have a negative correlation. When R is exactly 0, so it's actually equal to 0, we have no correlation or no relationship between the two variables. And when R is close to 1 to the data, we have a positive correlation. Now, the strength of the correlation can be determined by two different aspects. It can be determined by if you look straight at the scatter plot, or it can be determined by how close the R value is to 1 or -1 on either side. So if we're looking at the R value itself, let's just say I had it on a number line. Here's the best way to think about it. So I have a number line. -1 is all the way over here. 1 is all the way over here. And 0 is here in the middle. All right. If you're at 0, you have no correlation. All right. The closer you are to 1 is a positive. The closer you are to -1 is a negative correlation. Now, in terms of strong or weak, I like to look at how close it is to 1. So, like if you ignore the negative sign and you just look at the number itself, how close it is to 1. All right, the closer it is to 1, the stronger it is. So, my rule of thumb is that if it's 50% or higher, it's fairly strong, or halfway. If it's more than half, if it's less than half, it's pretty weak. All right. So let's say we had 0.5 here and -0.5 here. So what I would say is that if you had this is really, really close to 1 or -1, I would say that this would be the strong correlation. So more than halfway to either side, I would say it's a strong correlation. Whereas if we had it fairly close to 0, I would say that would be more of a weak correlation. So less than half, I would say it's a weak correlation. You can also look at it through its scatter plot. All right, so we'll come back to the example below this in a second, but look to the side of that same page where we have those 3 different scatter plots. All right, there are 3 ways to tell if your correlation is strong or weak or not at all. No correlation at all. It's called whether you have a hot dog, a football, or a cookie. All right. So we all know what all 3 of those things look like, right? All right. So how that works is if I drew a oval, circle, however you want to call it, around the scatter plots, just around the points in general. All right. So I'm just going to draw. All right. Which one does our left graph most resemble? A hot dog, a football, or a cookie? I would say a hot dog. Which one does our right one show? Football, cookie, or hot dog? Football. Looks a little wider than a hot dog, but it's not quite round enough to be a cookie. Otherwise, that'd be one messed up cookie. All right. What about this last one? What do you think? Cookie. Now, here's how they relate. If you have a hot dog, you have a strong correlation. That means that your scatter plot points are very, very close to your regression line. They're very, very close. They're very close together. If you have a football, it'd be a weak correlation because that means they're further away from the regression line. So there is some correlation, but it's not the best correlation. It's not very strong. All right. The relationship is not very close. And if you have a cookie, there's absolutely no correlation. It means that there's no way we could fit a linear function to it and be accurate about it. There's no true relationship between our 2 variables. Like, for example, if I was trying to graph the distance I drove in my car versus the distance I flew on a plane, does that really have any relationship to each other? No. So if I graph those, I would say that's going to have no correlation if I want to put a regression to it. They don't relate to each other at all. All right. They'd just be some random points on a graph. All right. Now, let's look more closely at these top 2. So on top of the strength of the correlation, we also want to look at its direction or whether it's positive or negative. What do you think about that first one, positive or negative? I would say it's positive. Why do you guys think that is? Because it's a positive slope. It looks like it's increasing. So we're going to say this is a strong positive correlation. What about the football? What do you think? Negative. So we're going to say this has a weak negative correlation. So that means our R value would be not very close to -1, but it's not at 0 either. Whereas the strong positive would mean that it would be pretty darn close to 1. All right, like maybe like a decimal place or 2 off. Now, if there's no correlation, that means the R value is exactly 0 and it doesn't have either a positive or negative direction. There's literally no direction. So if you have no correlation, if you have a cookie, your answer is just no correlation. All right. So let's do an example. So what I want you guys to do is, because you do know how to do this by now, I want you guys to take a minute and find the regression, either using Desmos or your calculator. So remember, if you're using Desmos, the function that you put in after you make the table, it will be different. And we talked about before, but just to remind you, you would put in y1 squiggle ax1 plus b if you were in Desmos. And if you were using your TI, all right, it's the exact same process as if you were trying to find the quadratic regression. The only difference is one button. So when you're calculating it, you would do stat right arrow key 5 for a quadratic regression. But now you would do a stat right arrow key 4 for a linear regression. It will literally say lin reg. All right. So make sure you hit the one that says lin reg. Yes, sir. Yes. Yes, ma'am.
Wouldn't we have the B1 and then plus C?
No, because that's a quadratic regression. So we want a linear regression, which means we have to put in a linear function. All right. We want it to represent a linear function. If we put in the x plus c, that would give us the quadratic. So that's the difference between quadratic and linear. It's a completely different graph type. All right. So take a minute, plot it in either Desmos or your calculator, whichever one you prefer, and see what you get. And let's say round to 1 decimal place. So round all your values in your regression to 1 decimal place. Yes, sir. Can you wait after you get through this question? If you need help with putting it in the calculator, just let me know, whether it's the Desmos or the TI. No, you do just the x. So guys, again, when you're putting in your values for your equation, look back at what you're putting in. So A, after the A would be just a singular x. After your B value, there'd be nothing there. It's just a constant. All right, so it's a little bit different than the quadratic ones that we did the other day. Because it's a linear function, not quadratic. You want it to look like a straight line, not a U. Yeah, this is not really long. Round linear is 10, so one is. So don't do the exponent. We're going to go and break up these questions. Yes, you said zero.
Oh, you're using extra. So you gotta make sure that these on here.
All right, guys, so let's compare some notes. All right. What'd you guys get for your regression equation? So what did y end up equaling? What'd you get for your a value? 0.15 or 0.2x, because we went around to the nearest tenth, so one decimal place. What was your b value? Negative 237.3. All right. So I did my regression in Desmos. So I put the table in first, and then I put in y1, x1 plus b. All right. So the red points is my scatter plot. The black line is your regression line. What do you think about the correlation? It doesn't ask us this, but what do you think the correlation is? So it's definitely positive. I heard positive. And it's strong. Why do you guys think it's strong? Right. Also, yeah. Also, look at the R value. So our R value is right here, the little r. Is this close to positive 1? Yes, it's very, very close to positive 1. 0.98, that's about 2/100th of a decimal place off from 1. So it's positive because it's a positive R value. And it is strong because it's very, very close to 1. All right. So that's a way you can tell whether it's strong or negative correlations. Now, we're going to use the line of regression to predict the life expectancy of a person born in 2015. So, what do I need to do using my regression equation to do that? First off, is 2015, does that represent an X or Y value for me? It is an X value because 2015 is obviously a year. If we look back up at our table, the year of our birth, that would definitely be our X value. So, what do you think I'm going to do with that 2015? Plug it in for X and evaluate. So, I would get 0.2 times 2015 minus 237.3. So, someone put that in their calculator and tell me what you get. Yep. So do all of it. Did you subtract or did you? Okay, you probably put something in there wrong. So if I did it, let's see. Did anyone else get a different answer when they put it in? So 0.2 times 2015. It's way off from where it's supposed to be. Okay. So let's just do a quick calculation together. So 0.2 times 2015 minus 237.3. I'm just going to put it in exactly. Yeah, you guys are right. 165.7. All right. So 165.7. Now, it may have just been the way we rounded. So I'm going to show you one where it's rounded to about 2 to 3 decimal places. That's something to configure. So let's try with a regression equation as, let's say our regression equation was y is equal to 0.157x minus 237.27. All right, try plugging 15 in for that and see what you get. So it's the same values that you already found. I just rounded it differently. Let's see if that changes an answer. So if I do 0.157 times 2015 minus 237.27, let's see if that changes my answer. Did anyone get an answer for that yet?
$79.1.
79.1. So guys, can you see how a couple of decimal places can really change your answer? Like these aren't even close. Same points that we got from our regression, same values, we just round them differently. So sometimes I would say that this equation is the better line of regression because it gives us an answer that's plausible. Because let's face facts here, guys. Do humans typically live for 165 years? No. All right. Unless we're like, back in the biblical sense. But way back in the Old Testament. But now, which answer makes more sense? The 79 or the 165? The 79. So I would say that this would be our better predicted value. So 79.1 years. Yes, ma'am. Yeah, you could say about 79 years. You can either round it to the 10th. You can really round it however you want. A lot of times you want to round in terms of what makes sense. So, like, for example, if you're talking about age, you may want to round to the nearest whole number. Years, it just depends on the context. So, yes, 79.1 years, that is a thing, but you could also just say about 79 years because that's what it's pretty close to. All right, so we're still not done with notes just yet, but we're going to take a quick 5-minute break and come back. So you guys can use the restroom if you need to, take a quick power nap, whatever you need to do. I'm going to go ahead and set the timer. Be back before the timer goes off.
Shit on the floor. Yeah.
All six of us have boxes. I don't. Oh. Oh.
Let's walk.
All right, guys, have a seat again. We're gonna pick it back up in about 5 seconds.
It just smells like.
Plug it into the, I think the one that's over there. Not really a power cord chain,
Right.
but then raise it so that blows it in the. All right, guys, so, shh. All right, so let's look at the last flap. All right. So we're gonna skip the first example on the last flap and go straight to the second one. All right. So the last flap, second example on the left. Come on, guys, I'm ready to start back up. So we're gonna make a very quick scatter plot of this set of points. That's all we're gonna do. We're not finding the regression, we're just making the scatter plot. All right. So I'm gonna have it go up by 25s on the side. So every 2 would be 50. And I can't count clearly. So it's on the line of regression flap, the last flap. Second example. No. I'll probably actually give you the lines of regression because I'm pretty sure y'all are fairly comfortable with doing that. So guys, we're on the line of regression. It's the last flap. We're looking at the second example on the left side. Because I shrunk it to fit in your journal nicely. So this will be 200, 250, and this would be 1, 2, 3, 4, and 5. So if I plot these points just very quickly, it look a little bit like this. So I'm just taking the points up top, and for time's sake, I'm just going to go ahead and plot them, and y'all can just copy it. All right. So, based off of where these scatter plots are, or the points are, what type of correlation do you think it's going to be? Strong positive correlation. So it does look like it has an increasing slope. And if I draw my little well, not really a rectangle. If I draw my oval-like shape, does that look more like a hot dog, football, or a cookie? Hot dog. So I would definitely say that is a strong positive correlation. All right, last one, and then we're done. So look at the top example of the second side. So to save time, because I'm pretty sure you guys are already comfortable with this, I'm going to give you the regression equation, all right, to save time. But is everyone pretty much comfortable with actually getting the regression equation? You guys fairly comfortable with it? So to save time, I'm going to give you the regression equation. So our regression equation would be y is equal to 4.82x minus 29.65. So using this predicted equation, how will I find when it's 90 miles per hour? So look at the table. Does 90 miles per hour, is that an x or y value? If you look at the top table, x. Because speed, which is in miles per hour, is x. Shopping distance in feet is y. Stopping distance, not shopping distance. Stopping. So this comes from, like, if you guys have taken driver's ed, you know how you need to stop a certain distance from the car in front of you to not nail them. All right. Basically, the faster you're going, the further back you should brake. All right. So if you're going like 55, you should probably brake further back from the stoplight than if you were going like 25, because obviously you got to account for the fastness. Yes.
Oh, no. I'm feeling a bit air.
Oh, I know. Like, it's working, just not well. Boys, quit. All right. So I'm going to plug in 90 in for x. So I have y is equal to 4.82 times 90 minus 29.65. So you put that in your calculator, what would you guys get? Right, we get about 404.15 feet.
In the parentheses, is that a 90 or 40?
90. Now, here's the kicker. When they calculated the actual shopping distance for 90 miles per hour, they found it to be 584 feet. Why do you think our predicted is so far off from the actual? It could be that, or look at how high the table goes in terms of speed. What's the highest speed listed on that table? 45. Isn't like 90 pretty far away from 45? Yeah, 45 is about half of 90, so we're a good distance away, whereas all the other points are within 5 miles per hour of each other. So this is what we call, this is a very special circumstance that the predicted is way, our predicted, guys, if you keep throwing that pencil, I swear, is way outside of the data set. All right. That point, 90 miles per hour would be an outlier to this set. It's way outside what we're actually looking at. All right. This is what we call, this situation is called extrapolation. And all that means is that since our value that we were trying to predict was so far outside of the values that we were initially given, those values could be, very close together, but then if we look at something that's way far out of it, it may not be as related as closely as we thought. All right. It's one of those things where we only know as much as we see. All right. We can't predict the future, so we only know as much as we see. So if our sight only goes to 45 miles per hour, if we were trying to predict maybe 50 or 55, even 60, it would probably be pretty close to the actual. However, 90 is so far away that it's outside, that it's almost an outlier to our set of data. Yes. Quickly. All right. Any questions on regression? All right, so you guys got a solid 25 minutes to work on your delta math for today. It's only 10 problems. It's mainly just finding regression lines and plugging stuff back in for X. Be very careful with how they tell you to round. And I'll unblock it in just a second. Just give me 1 second. Also, packet work would be pages 1 through 3, I believe, if you want to work on that too. So, Starbucks. All right, should be on block now. Yes. Sorry, say that one more time. You can do it during class today. After today, I'm not taking it because by the time I grade it by 4th period, it's done for unit 8. Okay. Because it was supposed to be due by midnight last night. Not today. All right, guys, make sure you're working. This goes for your calculator. It's going to be your friend. Oh my gosh.
80. Actually, doesn't even feel like 80. Wow.
Well, if we open the window, it ain't gonna help much because it's just as humid outside. So
But there's a breeze outside.
there's not a breeze anymore.
She's gonna climb down on the wall.
It's nice outside. It's like the same temperature as the little. Do you feel that? Does anyone else?
Give me a solid.
Yes, it's nice
Yeah,
outside.
solid. She just wanted to open the
You
window.
know what the column is? Is that what
She's fine. She just wanted to open the window.
it is nice outside. What if you just sit in the class outside?
Maybe tomorrow if it's still terrible. All right, guys, so make sure you're working on your stuff. Also, with this exit ticket, all I'm asking is based off of that scatter plot, do you think a linear graph would work the best, an exponential, or a quadratic? Basically, what does that scatter plot look like the most to you? Uh-huh.
We have an exit ticket yesterday.
No, because there was a test. I just had you guys fix the one from Tuesday.
I don't think I ever fixed the one.
Yes, I got yours. Yeah, I got it.
I got a 1 on 2.
Better question. Where'd I put it?
Like, you just write the answer, you don't have to show our work.
No, there's no work to show for that.
How do you show your work?
It's a yes or no question. It's not yes or no, but you know what I mean.
Oh, I thought you meant like that thing, the hot dog or something.
No, for this one, it's just doesn't look more like a linear graph, a quadratic graph, or an exponential graph. The ones we've been talking about all day today. Okay, it may have just been from the way you rounded. Nearest thousand. Yeah, that's 3 decimals, all right.
What did I tell you? Get back into my account. Yes. I love that. Yesterday. Oh, shut up. If I did, I would lose
What type of regression they want you to find? Make sure you put an exponential in there. So if you look at the 8.6, it's on there. I put that in. Boys, quit. It slipped. Okay. There it is. Okay. I knew I got it. Guys, so make sure that you're not just watching YouTube or something, you're actually doing your work.
And you still won't be there. I did try again so many times. Why is it looking so long? I think it's so long.
Oh, who had journals that they needed me to grade?
I did.
Bring it to me.
Kristen. It's not even letting me get it in.
Exponential. So
It says that quadratic is a part
exponential is this. Remember unit 6? Yeah, I said look at 8.6 because the Desmos, like I put exponential on there. It's this one, and then make sure that logarithm is checked out. So that's how you put it in. Desmos. Calculator, instead of 4 or 5, you hit 0. That's the only difference.
Oh, by the way, I don't know how I managed. I know you're not grading this stuff. I don't know how I managed to skip all this. Like this.
It happens. I'm not a huge stickler on stuff like that. As long as it's in there and I can easily find it.
You gotta close it up. Like, it's smaller than that, like that. I don't know.